So this represents the products, and this would be the reactants. Remember, going from left to right, and we have a reaction that's reversible. Equilibrium is about the reversibility of reactions. So I'm going to use this cup to go in the forward direction, and someone's going to use this cup in the reverse. In fact, I will do the opposite. Okay? I will take and use this cup. So I will represent the products becoming the reactants, and someone else will represent the reactants becoming the product. So this would be the forward direction of the reaction, and this would be the reverse. We've already learned if something is exothermic in the forward, it's what in the reverse? Endothermic. So now we have a reaction where both the forward and the reverse are going. Who wants to step up and help me? Kara, let's do it. So Kara, you're going to represent the reactants becoming products. Okay? So we're going to do equal cups, okay? So here we go. Fill your cup as much as you can. Okay? And you're going to pour your amount into here. So can you do it? You go? Yep, yep. And stay on this side, it's probably easier. So I go now. Now you go. Grab a cup.
With this?
Yeah, as much as you can. Okay, now you pour all of it, and I take a full cup and I pour. What's happening? Take a full cup? I'll take a full cup. What's happening? What's happening to the levels?
It's rising and then
Okay, so we can see that clearly. I'm going what? Faster in the reverse, aren't I?
Yeah.
Go ahead. So we're building up right. I want you guys to tell me when we're at equilibrium. Keep going. We're going to go equal cups at a time. Let it go. Equal cups. Here you go. Grab yours. And I'll go here. Whoa. Go here. Tell me when we're at equilibrium. Something's equal at equilibrium.
wait. I think you're equal.
A little bit more.
Equilibrium's strange because as we keep going, it looks like something doesn't change. So are we at equilibrium?
Well, you kind of
We
passed
kind of passed it. Let's keep going and see what happens. Equilibrium is going to get boring at some point. But we're going to keep going as forward reactions go and reverse reactions. Clearly, I'm taking more what? More water than Kara is. But somehow, we're still going to eventually come up with equilibrium. The forward rate and the reverse rate at some point are going to equal themselves out in this process. Didn't I start with more water than Kara?
Yeah.
Okay, and you can see as I got less because Kara had a smaller bucket. But at some point, we're going to reach equilibrium. We haven't yet gotten there. We're trying. Okay, now you guys thought, and everyone falls for it, that equilibrium is when the tank's water equal each other. That's not going to be the case. Equilibrium is never when the reactants and products equal themselves. Never. Equilibrium is about something about the rate of reaction, the forward and the reverse rate. Now, of course, it looks like we're going the same speed. We're going to look at rate as the amount of water. Now, what's funny about equilibrium is that once you reach it, it is boring. It looks like really nothing is going on. Now, you see our hands moving, but it becomes boring because at some point, nothing changes. If you've got bottled water, I see some bottled waters. If you keep the cap on, does the amount of water in the bottle change? No, because the rate of evaporation equals the rate of condensation. So it looks boring, but it's going on. Is this boring? Have I reached boring?
Yeah.
Yeah, I have, because we can keep doing this till the cows come home. I don't have any cows, so we're going to wait a long time. But we can keep doing this. Is our levels going to change?
No.
Are our levels changing anymore, I should say?
No.
No, they're not. Our levels are staying constant. What does that mean? That means we're at equilibrium. When the amount of reactants and products stay constant, not when they're equal, when they stay constant, keep going, we're at equilibrium. So it must mean something. I must be adding the same amount of water as Kara is because our levels aren't changing anymore. Correct?
Yeah.
Let's stop right now. And let's check this out. What did I say about the bottled water? Stay right there, Kara. I'm not sure. I say So you bottled water, here it is. If I keep a cap on it, that line doesn't change because the rate of evaporation equals the rate of condensation if the cap's on. That's equilibrium. The amount of water won't change. Me and Kara keep going. The levels of water, the amount of products and reactants stay constant because we must be adding the what? Same amount of water. Okay, now let me have your cup. Thank you, Kara. All right, now let's test this out. If we did this accurately, and I don't know if we did, if you notice, I started with the most water, and I had a bigger cup, and the bigger cup did what? Grab more water. So initially I had more what? I had more products on my side. But because I have a bigger cup, I was going faster. But then there was a point where the water got so low that I couldn't grab the same amount of water. So it should be, if we're at equilibrium, I should have the same amount of water I grab here that fills this cup. If this is equilibrium, this would mean that the levels don't change because Kara is pouring the same amount of water as this is in here. The only way to test that is do this. Here it is, grab some water. Now of course I was scooping like this, but if this is true, then the amount of water I can grab, I can't grab a full bucket because now it's too low, but if it's equilibrium, it's about the same. So equilibrium is when the rate of the forward reaction, when Kara and I were adding the what? Same amount of water back and forth. That's when we reached equilibrium. When the what? The amount of products and the amount of reactants stayed the same. So equilibrium, there's two parts to it. You know you're at equilibrium when the products and the reactants are constant, because the rate, as fast as I go in the reverse, I go in the forward. Okay? Let's do equilibrium, another demonstration. Okay? This time it's going to be me and Tom. Okay? All right, now what I'm going to use is I'm going to use something called film canisters. Okay, and I don't know if I can do it this way because I have to do this. So I'm going to use film canisters. Okay, and we're going to go a little down here. Okay, so me and Tom, we're going to have a little race here. Now, I don't know if you guys even know what film canisters are because you guys grew up with digital cameras, which is crazy to me. Okay, I learned photography with film and hoping I got the shot. Now it's like, oh, how did it come out? I don't know. So what we have is film canisters. Back in the day, we had these film canisters that we shot film with, and you actually put the film into the black container, and then you had to drop this off, and they did what? They processed it, and then you got back your negatives and the prints, okay? And it was a waiting process, okay? So here's what we're going to do. This represents a product, A and B. So let's put some together, okay? The job is going to be easy. Okay, what Tom is going to do for me is he's going to take and put the gray top to the black canister. And he's going to take reactant A, reactant B, and put them together to make the product. I'm going to be in the reverse reaction. I'm going to take them apart. Now, I want you guys to notice when we reach equilibrium. It's very important. Okay? You let me know when equilibrium has been reached. Okay, so we're going to have a race. Okay? I am going to break apart the products. Tom is going to put them together. He represents the forward reaction. What's the forward reaction? This is reactant A. This is reactant B. And in an arrow, we're going to make them bond together. Now, I'm going to go in the reverse. He's going to put them together. Don't know if Tom is up for the challenge, but I have done my small circles and my trunk twists. I am warmed up. Okay? So are we ready? Now I want you guys to recognize when equilibrium, when the rate of Grodsky breaking apart equals the rate of Tom putting them together. Okay, you ready? Go. Oh, hold on, stop. We have technical difficulties.
Jeez.
Okay, well, no one can see, but you're going to have to do the video. Okay. Technical difficulties, that's for sure. Hold on, Tom is cheating now. All right, so I have to go this way. I'll still record. I think Tom is enjoying the... I can't do it. So, okay, let's just go at it, and I'll show you the video. Okay, so Tom is busy putting these together. I'm taking apart. Who's faster? Who's the best? Who picked the best way to go? Okay. Just throwing stuff out, trying to get me all this disheveled. He's pretty fast though. Come on, Tom. I'm waiting. I'm waiting. He's holding on to them. Where are they? I'm waiting. I'm waiting. I'm waiting. I'm waiting. Okay, stop. Equilibrium was met, okay, when I had to wait for Tom. What was the faster way? Putting them together or putting them on? Taking them apart or putting them on? Was taking them apart, obviously I picked the right way. That's easier and faster. So Tom was slower putting them together. So I quickly caught up to him because my way was faster, but equilibrium was reached when I had to wait for Tom. Right? I took them all apart, and I was like, all right, got them all, got them all. Come on, Tom! All right, good. Come on, I'm waiting. So I was slowed down. I was fast initially. I did my tongue twist. And then I was waiting for what? Tom, eventually. That's when equilibrium was met. Okay, so, any case, you didn't quite see that. Tough cookies. Okay. So let's go to and see our class. Hey, shout out. All right, now let's get rid of this, and let's go to let's go to the worksheet I gave you. Okay, and I'm gonna get off of this source search computer. So the worksheet I gave you. Okay, so here we go, party people. Let's go over what we've learned so far.
No. Why? Mr. Grossi, can
It's here somewhere. I'll get it in a second. Okay. All right, here we go. In all of its glory. And we can all give a shout out to Jenny, who's home watching. Okay, maybe. Hi, Jenny. John, I don't like chemistry. Okay. John, I likes chemistry. All right, so let's go here. Okay, and we'll just rock it on right here. Good enough. Okay, so let's go through this. Now, I'm starting with my pen, and let's look at these graphs for a second, based on what we just learned. Is everything going to quit on me today? Looks like it. Okay, so let's make it bigger. Bigger. Okay, so look at my graphs here, party people. All right? I got A going to B, very simplified reaction. This reaction above is at equilibrium because what? Let's look carefully. I'm starting out with A. This is the concentration of A, the molarity. I'm starting out with a lot because I only have A. I have 0 B because it's going in forward. As the reaction goes forward, though, I create some B, but then the reverse occurs. Why is equilibrium achieved when these guys are flattened? Equilibrium is reached when the amount of reactants and products are not the same. They're not the same. See how they're not the same? When they're constant. Right. They were not the same in my demonstration. Only when Kara and I's tank, when they stayed constant, did we achieve equilibrium, because the rate of the forward equals their rate. So the A, you would say, because the concentrations were constant. The amount was constant. Write it. The amount of A and B were constant. That's important. Big word, constant. You will see that pop up like mushrooms on a wet yard. Okay? How else do I know we are at equilibrium? Look at the other graph. This represents rate, how fast. Because there was 0B initially, just like when I was doing the demonstration, I had a lot of mine and Kara had a little bit of hers, but there was a lot of A and very little B. But eventually, what equaled each other? How fast. Equilibrium is when the rate, how fast the forward equals the reverse. This is K of the F, this is the forward rate, this is the reverse rate. So equilibrium is when the forward rate equals the reverse rate. So you know you're in equilibrium when the amount of each stays constant, that's the straight line, or the rate of the forward reaction equals the rate of the reverse. Okay. In a water tank demonstration, when was equilibrium achieved?
When they were not changing.
Right. When the levels of water were, what's the word I'm looking for?
Constant.
Constant. Why? Because the rate, how fast the forward was going, in that case it was the amount of water we were pouring, equals how fast and how much water I was pouring in the reverse. Very important. In the film canister demonstration, when was equilibrium achieved? I was initially faster. I am so great at taking those things apart. When was equilibrium achieved? When I was going fast. I was going fast, and eventually I ran out of stuff, and exactly right. I had to wait for Tom, so I had to slow down, and eventually I went as fast as Tom made. He was the slowest leg, or the slowest, weakest link in this team, so I eventually had to wait for him. So, in the film canister, when was equilibrium achieved? When I had to wait for Tom, which equals what? The rate of Mr. G had to equal the rate of the slowest step, Tom. I guess you could put that as Y. Okay. Now let's get into some other examples of equilibrium that my demonstrations, based on those understandings, we can apply. Describe and illustrate solution equilibrium. Okay. Back when, I thought I had it still here. Okay. I took some potassium iodide and I put some lead nitrate and potassium iodide together, and when they were mixed together, they made a precipitate. Now, if I've got some solid in the bottom of my precipitate, here's what's actually happening. So I want to illustrate this together. So in our beaker, let's draw a beaker. Everyone draw a beaker. Now in my beaker, I've got some solid. Now our solid is yellow, so make sure you draw yellow. Just kidding. Okay, now I have the yellow lead iodide. That's what this is. That's what this is. Lead iodide, PBI. Now it doesn't dissolve much, but this is what you have to know. Very important. If it is in equilibrium, watch the reaction. PBI2, solid. Notice, party people, I put a double arrow. Becomes Pb plus 2 iodine ions. Now both of these are aqueous. Or as we say in West Hampton, aqueous. I've got some aqueous. Okay.
Why is it double arrow? Because it
Double arrow is saying to you that we can go forward, hey, or reverse, hey. We can go both ways. So what I'm telling you, if we're at solution equilibrium, we are dissolving the solid right here. The solid is dissolving into Pb plus 2 ions, or iodine ions, right? Or the ions are coming together and doing what? Going back and reprecipitating. Let me explain. We have the solid breaking apart into ions. That's dissolving. That's this way. And we also have some going back. That's what equilibrium means. Yes?
What would be like a question we get for this?
I'm gonna tell you in a second. If we're at equilibrium, the rate of dissolving equals the rate of reprecipitation. Here's the question. How much solid is the solid amount going to change? If I have 10 grams of undissolved solid and I'm at solution equilibrium, how many grams do I have a day later? Same, because I'm at equilibrium. Here's another question. In order to be at equilibrium, this is the most important question that will pop up. If I'm at solution equilibrium, the rate of dissolving equals the rate of precipitation. The only way you get the reverse if you have a certain kind of solution. Think with me for a second. This room holds 400 people. Let's pretend there's 2 open doors. If I put 400 people in here and there's 2 open doors, and I take Jackie and I jam her in, okay, what's going to happen out the other opening? Someone's going to fly out. That only works if the room is saturated. So if I push some of these ions this way, it should push some back. That's the only way this works. So describe the solution for me. Is it supersaturated, unsaturated, or saturated? Was the room holding the maximum amount of people? Yeah, the only way you can push Jackie in and push some stuff back out is this solution has to be saturated. Put a circle around it. You're going to see it. It's something you'll see on a region. This solution, and I'll make it so you can see it, understand it, must be saturated. If it's not saturated, party people, if it's not saturated, the rate of what? Dissolving will go forward. If the room has no people in it and I throw Jackie in, she won't fly out. I can throw 399 more of her friends in until it happens. This is saturated. That's important. Does that make sense? You can't have it going in reverse unless you have no more room. Okay. Describe and illustrate melting freezing phase equilibrium. Party people, we've studied this already. We just haven't looked at it this way. Remember the heating and cooling curves? Hey, going up. Then you become a gas that keeps going. Okay, here's my solid. Here's my liquid. Here's my gas. And what do we have? A solid in equilibrium with its liquid. If you talk about this phase change right here, sometimes they'll say, hey, where is there an equilibrium of 2 phases? Okay, solid or melting and freezing can occur at 0. So let me set this up for you. I have the world's best cooler. In my cooler, no heat gets in. Now, it's an impossibility, but that's what I'm saying. I have some Vasa in it, water. Now, floating is, I did a self-portrait as an ice sculpture of my head. Okay, I got a blockhead, I guess. Okay, now it's floating. I come back, and I put the cover on. I come back 4 days later. I come back a year later. There's still the same amount of ice if no heat gets in. Why? The rate of what is equal to the rate of what? The rate of melting from a solid is equal to the rate of refreezing. Hey, that's equilibrium. How would I write that? H2O solid, double arrow, H2O liquid. Now, if no heat gets in, the amount of ice stays constant. Now, it's impossible. Eventually, it gives way. but the shape of my head disappears over time because of the what? The refreezing in different positions. Number 6, describe and illustrate vaporization phase equilibrium. My friends in chemistry, phase equilibrium of this one is up here. We have what? A liquid in equilibrium with a gas. So if they ask you where the boiling or the vaporization condensation phase equilibrium is, it's up here. Or if they can ask you on a test, given a heating curve, where is there an equilibrium between the liquid and gas? Right up here. And it's easy to illustrate, party people, because let's draw the water bottle. Got myself a bottle of water, and I got it capped. Guess what? The rate of vaporization is equal to the rate of condensation. What does it look like? H2O liquid, double arrow, becomes H2O gas. And if you keep the cap on, what can you say about the level? It stays constant. You never have a closed bottle evaporate away. It's because of the equilibrium, the evaporation and the condensation doesn't stay constant. Now open the top, game is over, the rate of evaporation is greater. Now, last question, and all of these are the most important you have to know. Will a catalyst change equilibrium? Well, let's think about this for a second. Here we go. Here's my phase diagram. Here's my potential energy curve. What does a catalyst do? Lowers the activation energy, right? So if I add a catalyst, doesn't it lower the hump the same for both sides? So adding a catalyst would speed up the forward reaction as much as it would speed up the reverse. So adding a catalyst has what kind of effect? No effect. That's, my friends in chemistry, I just hit everything that you needed to know for this course. No effect. Why? It speeds up the forward reaction as fast as the reverse. Let's do number 8. Which statement describes a reversible reaction in equilibrium? You need the decoder pen for that. The rate of the forward reaction must equal the rate of the reverse reaction. The concentration of the reaction must equal the concentration of the products. Which one describes a reaction equilibrium? 2, the rate of the forward equals the rate of the reverse. Number 9, which statement describes a chemical reaction at equilibrium? The products are completely consumed. The reactants are completely consumed. The concentration of the products and reactants are equal. Is that it? No. The concentrations of the products and reactants stay constant. Okay? So, homework. Do number 10. And I would like you to work on the conclusion questions. If you finish your conclusion questions tonight on your lab, there is no conclusion. So if you hand it in tomorrow, no conclusion. If you do not get it done, I want a conclusion. See you tomorrow. Number 10, we won't do. Your homework is to watch a lecture and work on the other worksheet. Have a great day.